Welcome back to this next video in the playlist on Galois theory. In this video we're now going to prove the other side of the theorem that we needed in the video on solvability by radicals. Namely, we're going to prove that in the case of characteristic zero fields, that if you have a finite solvable extension, that it's always contained inside a radical extension. And then once we've done this, we will have proven the two things that we needed in that video, and that will then be our proof complete for Galois' characterization of when a polynomial is solvable by radicals over a characteristic zero field, and therefore our argument as to why there will never be a quintic formula will then be complete. Good. So again, we have a field f which is characteristic 0, so characteristic of f is equal to 0. And let's say now that we have a finite solvable extension that I'll call S. So this is an arbitrary finite solvable extension. And I need to now show you that this is contained inside some larger extension of f, which is a radical extension of f. So the first thing I'm going to do is I'm going to use something that we know about finite solvable extensions. We know that they are built out of a tower of cyclic extensions. So I'm going to put that tower of cyclic extensions here. So we'll have, what should I call these? We'll subscript it. So we'll have f being f0, we'll have s being fn, and then we'll have fn minus 1 here, fn minus 2 here, etc. And then f1 will be the first one here, and it will go up. So you've got this tower of cyclic extensions inside the overall extension from f to s. And these are all cyclic. Now all of these have a degree, so let's give those degrees a name. So we'll give the degree of f1 over f0, we'll give that the name m1. We'll give the degree of f2 over f1 the name m2, and then it will go all the way up to mn, which will be the degree of fn over fn minus 1. Now what I'm going to do is I'm going to define overall m to be m1 times m2 all the way up to mn, so the product of all of these degrees, which would then, of course, be the degree of s over f. If each of these things has, if this extension has degree m1, this extension has degree m2, all the way up to mn here, then the overall extension s over f has degree m, which is equal to the product of all of these. Fine. So what am I now going to do? So I want to try and show that my solvable extension is contained inside a radical extension. Radical extensions are made up of a tower of simple radical extensions. So I need to try and produce something that is going to be built out of a tower of simple radical extensions. I know that Kummer extensions are all simple radical extensions, and I also know that cyclotomic extensions are all simple radical extensions. So if I could build something that's built out of Kummer extensions and cyclotomic extensions, I'd be in business. I'd have a radical extension. These extensions are all cyclic. That's quite suggestive. I know that if I have a cyclic extension of degree n of a base field that contains a primitive nth root of unity, that will be a Kummer extension. So my idea now is to add on all the necessary primitive roots of unity that I need, and then to take the compositum. So what I'm going to do is I'm going to create the nth cyclotomic extension of f, which will then have a primitive nth root of unity in it, and therefore will have a primitive m1th root of unity, a primitive m2th root of unity, all the way up to a primitive mnth root of unity. So it will have all the necessary primitive roots of unity. This will, of course, be a finite extension. It will be a Galois extension. We don't actually need the fact that it will be a Galois we do need the fact that it will be a Galois extension. But finite is actually going to be more important to us. So what I'm now going to do is I'm going to take the compositum of S, my original solvable extension, with the nth cyclotomic extension of F. Now, because they are both finite Galois extensions, this thing that I produce up here will actually be a finite Galois extension because it's the compositum of two finite Galois extensions. So there'll be a finite Galois extension of F, but I don't actually need that because what I want to show is that it's a radical extension of F, and this will be the radical extension here in my theorem. And radical doesn't require it to be finite Galois. So what I want to show is that it's built out of a tower of simple radical extensions. So this first one, this nth cyclotomic extension, this is a simple radical extension because it's achieved by joining on one of the primitive nth roots of unity, which is a radical. So this is a simple radical, so that's good. Now what I want to do is break up this one here into a whole bunch of extensions that are simple radical extensions. And the way I'm going to do that is by translating all of the sub-extensions that I've got here over to here. So again, I'm going to use a little bit of Galois theory, basic Galois theory that I'm not going to prove here, which is about what happens if you translate a finite Galois extension. So this is what I'm going to use. I'll just state this theorem here. So if you've got a field F and you've got a finite Galois extension K, so this is finite Galois, and then you've got another extension, we'll call this K1 actually, and we've got another extension K2, and we don't need this one necessarily to be finite Galois. In the case of this example here, this one actually is finite Galois, but we just need it to be finite. So if this one is finite, then if you take the compositum of K1 and K2, then there is a theorem in Galois theory that says that this extension here, the extension K1, K2 over K2, this will also be finite Galois, and furthermore, that its Galois group, so the Galois group of K1, K2 over K2, that it will be a subgroup of the Galois group of K1 over F. So that's what we're going to now apply. We're going to apply that, so for example, we're going to take F1 over F0, this extension here, this is a finite Galois extension, it's a cyclic extension, so its Galois group is cyclic. We're now going to translate it over here to take the compositum of F1 and the nth cyclotomic extension. So we've got F1, Fm, like so. And I can now conclude that this is a finite Galois extension with Galois group a subgroup of the Galois group of the original thing. Now, cyclic groups only have subgroups that are also cyclic, so that means that this is forced to still be cyclic, and moreover, its degree is going to divide M1, because, you know, this had Galois group CM1, subgroups of it are going to be cyclic, and they're going to have order dividing the order of this one, dividing dividing M1. So it's going to be CD1, let's say, with D1 dividing M1. And then we continue. So we can now go up further. So we can go up to F2, the compositum of F2 with the nth cyclotomic extension of F. And again, this will be equivalent to the compositum of F2 with the extension below it, so F1 compositum Fm. You know, they are equivalent. This means the smallest extension that contains all of this, F1, Fm, and F2, but that's the same as being the smallest extension that contains F2 and Fn, because the moment you contain F2, you contain all of F1 anyway, so it's a trivial condition. But the point is that seeing it as this, seeing it as that compositum of those two, that's quite helpful because we know this is a finite Galois extension, so now we use our translation theorem to say that this will now be a finite Galois extension, and its Galois group will again be a subgroup of the Galois group of the original extension, and therefore it will be CD2, where D2 divides M2, for the same reason as what we've argued before, that cyclic groups have only subgroups that are cyclic, and those subgroups will have order dividing the order of the original group. And so this continues, and what we're going to have overall here, going all the way up to so Fn minus 1 Fm, is we'll have a whole bunch of cyclic extensions where the degrees of those cyclic extensions divide the degrees over in the original tower of extensions over here. Good, so what I've now produced then is a tower of subfields, sub-extensions going up to my overall extension SFM here, and they're all cyclic extensions. Now we use our knowledge of Kummer extensions. So this has an m1th primitive root of unity, it has an m2th primitive root of unity, it has all the way up to mnth primitive roots of unity. And these d's, these divide these m's, therefore this extension, this cyclotomic extension, it will contain a d1th primitive root of unity because of the fact that it contained an m1th primitive root of unity. Similarly, it will contain a d2th primitive root of unity because it contained a primitive m2th root of unity, and so on. So because di divides mi, you can conclude that all the necessary primitive roots of unity are here. And now we just use our knowledge of Kummer extensions to say that we now have cyclic extensions of a certain degree, and we have a primitive root of unity of that order in our base field, and therefore these are Kummer extensions. Brilliant. So we've now got a tower of Kummer extensions. We know that Kummer extensions are all simple radical extensions, so we can therefore conclude that every single one of these extensions, and I'll highlight them in blue here, so this one, etc., all the way up to here, all of these are going to be simple radical extensions, and therefore this is built out of a finite tower of simple radical extensions, and ergo is radical. And that completes the proof. That proves that starting with an arbitrary solvable extension of a characteristic zero field, that we can create a larger extension of the base field that contains our solvable extension, our finite solvable extension, which is radical. And that then completes our proof that we needed, or completes the proof of the two things that we needed in the video on solvability by radicals, which then completes our proof that there will never be a quintic formula. So I hope you've followed the entire argument. If you've made it to this video, thank you. We'll end it here.